Swayam Prabha. Digital India. Educated India.
Hello friends, welcome to the week number 5 of our MOOCs course on the topic of principles of mechanical measurement. Over last 4 weeks we have set up all the initial topics that we need to know about this topic of measurement. Like we have discussed about the basic characteristics of the measurement system, both static and dynamic characteristics. We have developed generalized mathematical model and tried to see how we can solve those mathematical models to get idea about the characteristic of the systems. We have primarily discussed about the zeroth and first order instruments and also a bit about the second order instruments. Then we have also discussed in the previous week about the output data or processing the output data. In the very first week itself we have discussed about how to analyze or identify the error that can be present in the output that you are getting from your instruments. So with all this knowledge and of course I should not miss the very interesting topic of digitalization that we have discussed in week number 3. So with all these concepts, now we are ready to discuss about individual instruments which are suitable for measuring particular parameters. And the first one that we have in this chain is displacement or distance. So in every week from this one onwards we are going to talk about the measurement of any particular parameter. Like displacement here, then we shall be talking about velocity or motion measurement, force and torque measurement, pressure, temperature, flow, etc. one in 1 week. And the first one in this line is displacement, which is probably the most fundamental among all the parameters that we are going to measure. Actually the term displacement we are going to use here to represent any parameter having the dimension of length, such as say the dimension of something, or the displacement or distance covered by something, or maybe the strain, anything having a dimension of length. And immediately you can get the idea that we are talking about a very wide length scale. The displacement or distance measurement can involve something at the molecular level, say the radius of a particular molecule, or say the diameter of one molecule, or maybe the distance between different electrical orbits that we can have inside a molecule, etc. That can be one way, or slightly larger than that, the mean free path of the molecules, which can be very important in any kind of statistical appraisal of molecular dynamics. Or we can be talking about extremely large length scale, that is the diameter of a planet, diameter of the earth, maybe the radius or the diameter of the orbits of any particular planet which is moving around the sun. Maybe we may be talking about light year. Light year is very confusing term because as the term suggests, or as the name involves a year, it immediately gives an impression of being an unit of time, but actually it's an unit of length, because all of you know definitely that light year refers to the distance travelled by light in vacuum over a period of 1 calendar year. So it is also a unit of length and a huge unit of length that we are talking about. On the contrary, we may be talking about angstroms and even much smaller units than that when we are talking about molecules or intramolecular matter. And therefore the topic of displacement or distance measurement can involve a very wide length scale, and they can be important in innumerable number of engineering applications. We can talk about any kind of velocity measurement or motion measurement, and that will always involve an estimation of the displacement, because to measure the velocity of something you need to know the distance covered by that particular item over a particular period of time. So you have to measure the displacement and you have to measure the time, and you will get the idea about the velocity. Similarly, measurement of several other parameters are actually or fundamentally can be reduced to the measurement of displacement. Like just think about the example that we are talking about from the very first class, how we measure temperature using a mercury thermometer or such liquid in glass thermometer. we measure the displacement of the mercury column within a capillary tube. So, what actually measure is a distance. Now, that it is a different thing that the scale of distance is given in terms of temperatures, we can directly get a temperature reading, but the fundamental parameter that we are measuring there is displacement or the change in the length of the mercury column. Or how we measure some pressure or differential pressure using a liquid manometer. We basically measure the difference in height between two columns of liquid, and then that is calibrated in terms of some kind of pressure quantity. So, again the measurement of displacement gives us the measurement of pressure. Most of the transducers or electromechanical transducers, they work on the principle of measurement of displacement, or I should say whatever parameter we are trying to measure, generally that is converted in form of some displacement, and then it is converted to some electrical quantity to get the final output. And that is why the concept of displacement measurement is extremely important, and that is the primary reason that we are taking this one as our first parameter. Now, all of you know that the fundamental SI unit of displacement is meter. In SI unit at present we generally define 7 parameters as fundamental quantities, and distance is one of them. So, meter is the unit, but how much is 1 meter? How much length do we refer to as 1 meter? That particular definition that kept on changing throughout the history. Like if we just look at the figures or numbers that we have here, like in the year 1790 or around that time, that is the time before SI unit was standardized, people are mostly concerned about the use of the CGS systems, or the use of metric system has just become popular, just started to become popular compared to the fundamental English units. So, during that time 1 meter was defined as the length of a pendulum that swings half of its maximum distance in 1 second. So, by measuring the half swing period as 1 second, whatever length we get, that is 1 meter. But it soon changed to define the value of 1 meter in terms of some distance along the periphery of the earth. Actually, it was measured as the distance between the North Pole and the equator, and 1 by 10 millionth of that distance was identified as 1 meter, because the distance was measured as approximately 10 million. That again changed very quickly. Around 1795, a length of an official bar of brass was fabricated to be exactly 1 meter. That soon changed in 4 years times, where instead of brass a bar of platinum was used, and the length of that platinum bar was measured in terms of the brass bar. One of the reasons for going for platinum was that it has extremely less wear and tear compared to brass, and that particular platinum bar was stored in French National Archives, and it was there for about, it was the standard for about 100 years. Now, in 1889, basically about 90 years since the platinum bar was identified as a standard, now 2 lines on an official bar of platinum iridium alloy, or I should say the distance between two fixed points on a platinum iridium alloy bar was identified as 1 meter, and that was measured at 0 degree Celsius in order to avoid the thermal expansion of the bar. Platinum iridium is a very hard material which hardly suffers any kind of erosion over long period of time, and therefore, it is able to maintain this length over a significant period of time. In 1927, now the previous standard was slightly modified, the bar remains the same, and the standard atmospheric condition was still maintained at 0 degree Celsius. However, now the bar was allowed to rest on 2 1 centimeter diameter cylinders, each of which were 5 centimeter 571 millimeter apart from each other. But all these cases you can find that, particularly starting from that brass bar, that you can find that the standards that we are defining, they are not absolute standards, truly speaking. And so, scientists felt the need of identifying some natural phenomena or defining the value of meter in terms of some natural phenomena or something more fundamental, which does not suffer the effect of aging or wear and tear or some kind of mechanical error or the effect of temperature kind of things, etc. And therefore, in 1960, krypton 86 alloy atom was identified, and the wavelength of radiation when it gets in vacuum, when it gets transited from this 2p10 to 5d level, that was used as 1 meter. So, but that soon changed, and the present standard, which was defined in 1983, where the length travelled by light in vacuum over this period, or I should say the length travelled by light in vacuum over 1 second, this particular fraction of that is defined as the value of 1 meter, and this is the present standard that is still followed. It is a very fundamental quantity. It hardly suffers any change, or there is very less chance of this one to get modified because of any other external factors, and therefore we can consider this one to be a very fundamental quantity or fundamental definition of meter. Now, with this we can move on to study a few of the instruments which generally uses or generally measures the displacement. The first that we are going to talk about is gauge blocks, which basically are standards or the or the option that is used generally for calibration of the devices, and then we shall be discussing about a few transducers. Here in this module we are mostly going to talk about electromechanical transducers, that is where the displacement is modified to some electrical quantity, and that electrical quantity is measured and calibrated back to get the displacement. But we shall also be talking about a few other kind of transducers for measurement of the displacement. So, first we have the gauge blocks. I am giving both the spellings depending on which kind of English system that you prefer, the British English or the US English, but the first one is the one that I am going to follow. Gauge blocks are the industrial standards for calibrating any kind of distance or displacement measuring instrument. Even starting from a simple ruler to very complicated laser based instruments, all of them can be calibrated in terms of gauge blocks. Of course, there are several other excellent calibrating options, but gauge block is the one generally which is preferred in industry, primarily because of its simplicity. They were first proposed by C. E. Johansen in 1896, and that is why they are often called Johansen block as well. Gauge blocks are metal or ceramic blocks with two opposing faces ground precisely flat and parallel. That is, we are talking about something, a block, a 3-dimensional block like this, generally of rectangular cross section, but its cross section can be something else also. Here two opposing faces like this particular one and the one below this, they have to be extremely flat, and then the thickness of this particular, or I should this particular thickness of the block is the one that we are concerned about to get the measure of any particular length. So, gauge blocks generally come in sets. Standard blocks are made of hardened alloy steels, something like WC. Can you guess what is WC? What W is a symbol for what? It is tungsten. So, WC is tungsten carbide, and there can be chromium carbide as well. There are several kind of chromium carbide that we can identify. So, I have given a few of them. So, tungsten carbides or chromium carbides are very hard alloy steel which hardly suffers any kind of erosion or wear and tear, and that is why they are generally preferred as the material for forming these metal blocks, and we can of course have ceramic blocks as well. They are characterized by ultra flat surfaces, and these blocks are joined together following a phenomenon known as ringing. I shall be talking a bit more about ringing shortly. Actual length of each block is generally shorter than the nominal value of the thickness. Like suppose if this is one block and it is given that the length of this block or nominal length of this block is 1.1 millimeter, actual length, or I should say this particular dimension of the block will be slightly shorter than 1.1 millimeter, because say if we want to join this particular block with another one or maybe a few more to measure slightly higher length, then the blocks will be placed like this, one on top of each other, fitting exactly with each other via the process of ringing. Now, between these two blocks, means I am talking about this particular interface or this particular interface, we generally have a very thin film of some lubricating oil, and this lubricating oil, or often referred to as the ring film, the thickness of the film also you have to consider while taking the final reading, which is like this. So, if each of these blocks are having exact value as whatever given on their on their specification, then the final reading that we are getting here, that will be slightly larger than what actually it is, what is given by the gauge blocks, because of the presence of these two sets of lubricating oil ring flames. Therefore, the nominal value, each blocks are generally made slightly shorter than the nominal value of the thickness of one ring film, and the thickness of a ring film generally is very small, just about 25 nanometer or thereabout, so that when two blocks are joined together like this, then we may have a film of 25 nanometer in between, and therefore, the value dimensions of both of these blocks, that is this particular dimension and this particular dimension, both takes care of this ring film, and therefore, the final, when we take this measurement, we get the exact value, because this 25 nanometer thickness of film is being taken care of while fabricating the blocks themselves. They come generally in this is the way generally they look like. The gauge blocks and a small ring film, extremely thin thickness of ring film. The height of the blocks are often referred as interferometric length as well, and the blocks, instead of the platen, they can be joined with each other with this thin film of blocks in between. This is how a typical set look like. This is a very standard company picture from a very standard company, and you can see there are so many blocks with different dimensions. Like the smallest one in the set that I am showing is having a value of 2 millimeter, whereas the largest one is having 100 millimeter, and some of them has been repeated as well. Just you can see here, there are two blocks having dimensions of 2 millimeter. So, we can join them with each other to form any particular dimension. Like suppose you want to measure a value of say 5.48 millimeter, or I should 5.48 millimeter is the one that you are trying to measure. Then what are the gauge blocks that you should go for? There are several combinations that you can always go for, but generally we would like to go for something which gives us the smallest number of blocks. So, there are two ways you can go for, like what is the smallest dimensions that we are mostly bothered about, that is this 0.48 is something that is we have to be concerned about, that is the smallest possible or I should say 0.08 millimeter is has to be the smallest possible value that we can use, but there is no 0.08 millimeter, actually we are starting only 2 millimeter. So, let us try to identify something which has this at the 0.08 millimeter as the last digit. We are lucky here that 2.48 is there. So, we can choose 2.48 as one. So, let us take 2.48. Then what else we can go for? We can take a 2 millimeter and we can take another 1 millimeter. So, 2.48, then 2.00 and 1.00, these three together will give you 5.48 millimeter. So, we can join these three blocks and get the final value, or if we are trying to measure the values of any unknown dimension, then we can keep on adding or stacking these blocks one on top of another and try to match when we get the exact comparison. So, finally, getting the values of these blocks or adding the values of these blocks, we get the final dimension. Each country has their own standards. The blocks can have different kinds of categories, like very commonly you will find categories such as AA category, A category, B category, etc. AA being the most precise one with extremely small level of error, something in the range of 0.01 micron or even lesser, whereas A or B are having slightly larger uncertainty in their predictions, but typically the tolerance value varies between 0.01 to 1.3 micron across different countries. And this is how gauge blocks can be stacked up. You can see there are so many gauge blocks that we have stacked up to get a final value, and once they gives an exact comparison, then by joining their values we are getting the final reading. But the way these blocks are stacked up, that particular phenomenon is called ringing. As I have mentioned, like we have said, this is one block and this is another block, and in between somewhere these blocks are joined with each other. And don't feel that it is something like stacking bricks on one on top of another, or just boxes one on top of another. Rather, this is a very strong bond. Instead of having the blocks this way, we can most cases we can also tilt the blocks this way, and they will still be still remain joined with each other, almost like magnetic attraction. So this phenomenon of ringing is the one that is responsible for this. Unfortunately, there are several theories behind the appearance of ringing, and we are yet to reach any particular consensus, but some of the common cause or common mechanism for ringing can be mentioned. One can be the air pressure, because when two blocks are coming in contact with each other, the air from the intermittent space or intermediate space that goes off, and as the air is squeezed out, that surrounding air creates a very high pressure on this, allowing this phenomenon of ringing. A more reasonable reason, or I should say a more a better reason, can be the surface tension because of the presence of oil and water vapor in the gap. The molecular attraction can also be a reason. When two very flat surfaces are coming in contact with each other, the cohesive forces of the molecules of the metallic alloys or metallic ceramic alloys which are there, that can also lead to very strong bonds. These are some of the reasons, the surface tension and molecular attraction based theories being the most common one, but I repeat, there is still no consensus about why ringing happens. But ringing do happen, and these blocks can stick to each other, forming very tight bonds. This is generally the way the blocks are placed on top of each other. Like this is our block number 1, and we want to put this block number 2 on top of this. Then generally the blocks are, the second block is placed perpendicular to the first one, and it is slide with pressure on top of the first one, so that the air is squeezed out of this. And now once we reach this cross kind of position, then this is rotated in a particular clockwise or anti-clockwise direction till we get a perfect match like this. And once they are into this particular position, it will be a very tight bond, just we have mentioned. One big problem with the use of gauge block is that being made of metal, they suffer from the problem of thermal expansion. As the temperature changes, their length can change, and therefore they can give accurate reading only at the value at which they have been calibrated or they have been fabricated. So maintaining the temperature is extremely important while using the gauge blocks. Several options are there. One option can be the use of air conditioned gauging rooms. Now using it may not be possible always, like if you are trying to measure something related to an industrial process, we have to get the gauge blocks to that particular location. And also suppose we want to measure the length of one particular sample, now we take it inside the air conditioned room where the gauge blocks are there, but generally the parameter, or I should say the component whose length you want to measure, that itself may take 10 to 15 minutes or even more time to come in thermal equilibrium with the room itself. So you have to allow that amount of time. Second option can be use of a constant temperature bath made of kerosene or certain non-corrosive liquids. The gauge blocks will remain immersed into this, and while taking the reading, they will be taken out for a very short interval. Readings will be taken, and immediately they will go back to the pool of liquid. If we are looking for a very precise instrument, then our specimen or the subject itself can also be immersed, and entire measurement can be done in the immersed condition. But again, that may not be possible in all scenarios. So in that case, when we can't allow an air conditioned room or we can't do the measurement in submerged condition, then we can make use of the theoretical correction factors. Like suppose if we know that the length of the block is L at the standard reference temperature T naught, and we are actually taking the reading at some temperature T1 which is higher than T naught, then if we have complete idea about the properties of the metal which are being used to fabricate this block, then we know that at this temperature T1 the length of the block will be L into 1 plus alpha into T1 minus T naught. So, this will be the modified length. So, but actual reading will be shown for L only. So, we can by having a knowledge of this temperature T naught and T1, we can correct this value of L to get back to this L1 and thereby getting the exact length of the subject. So, this way gauge blocks are used in industries to calibrate different kind of measuring devices and sometimes also for direct measurement of dimensions. Now, the first instrument that we are going to talk about, first kind of electromechanical transducer that is based upon the electrical resistance, and that is known as the potentiometer. Do you remember this term where we have used earlier? If you remember correctly, potentiometer is one of the example of a zeroth order instrument where we have made use of this name. Its working principle is very simple. As we know, the resistance of any resistor R is equal to rho into L by A, where L is the length of the resistor, A is its cross section area and rho is the resistivity, is a property of the material. Now, if the resistor is made of uniform cross section and also if the material properties remain uniform, then R is directly proportional to L. So, as the length changes, resistance will also change, and accordingly we can get a measure about this length. Just like the arrangement shown here, generally the potentiometer, sometimes also called rheostats or in short pots, they are connected with a voltage source, commonly a DC voltage source, and then this is the resistor over which we have a slide in contact which keeps on moving along this. This sliding contact is connected to the location where we want to measure the displacement, and now as the sliding contact keeps on moving over the resistor, the corresponding output voltage that keeps on changing. As you can see, R is the total resistance, but the output is connected only to this R2 portion. So, what will be the relation between your output voltage and the supply voltage? So, your output voltage divided by your supply or excitation voltage should be equal to R2 divided by the total resistance R1 plus R2 or R2 by R, and resistance being proportional to length. So, this length can be L2 upon L, where L2 we are referring to as this particular length we are talking about L2, and L is the total length of the resistor. So, by measuring this voltage V out, we can directly get the value of this resistance or output length L2, or we can say L2 becomes equal to V out by Vx into L, or can say I can write this way, V out by Vx by L. This Vx by L is called potential gradient, which is Vx by L, generally given by a K, but it is non-standard symbol. You can use any other symbol for this potential gradient also. What this is looking like? This is sensitivity of the instrument. Longer the length for a given value of Vx, so the higher will be the precision of the measurement, and as the length changes, resistance will also change, and so for small change in resistance, small change in length, you will get a larger change in resistance, and accordingly a larger or more significant change in the value of V out. So, this is the working principle of potentiometer. Ideal potentiometer is a perfect example of a zeroth order instrument, as there is no storage properties and output and input are linearly related, like just like here, this V out is the output, Vx is the input, and we get a very straightforward linear relationship, something like this. The resolution of the instrument, which is strongly depends on the construction of the resistance element itself. Depending on what kind of resistance elements you are putting, we can have different kinds of potentiometers. Like one kind of potentiometer can be just the one that is shown here, that is linear potentiometer, or sometimes called single slide wire potentiometer, where you just have one slide wire like this and the contact keeps on moving up and down over this. Initially, if say, like if I go back to the original diagram, if the contact is connected to this particular position, then your entire resistance is available to the output. So, V out will be equal to V x. However, as the contact keeps on moving down, as the displacement happens, corresponding V out also keeps on changing, and when the contact reaches somewhere here, V out will become equal to 0. So, this is single slide wire potentiometer. However, if we can if we are looking for measurement of angular deflection, I have not talked about angular deflection so far, but remember, whenever you are talking about deflection or displacement, it can be linear, it can be angular as well. We shall be discussing about a few specific instruments for angular deflection measurement towards the end of this module, but potentiometer can also give us that option. To make a resistive potentiometer to give angular deflection, we can measure the potentiometer, or the resistor can be given a shape like this, where voltage are measured along this, and the slider, this is the initial position of the slider, and that keeps on moving along this, and therefore, its angle of rotation is a direct measure of the resistance, and or I should say the other way, the resistance is a direct measure of the angular deflection, and accordingly this output voltage is a measure of the angular deflection. And instead of one, we can also have multiple turns if we are looking for very large resistance measurement or large deflection measurement, where we can form the resistor to form such kind of helical structure to give the voltage. These are the two ends, and this helical structure allows the contact, or I should say the sliding contact to move over a very long resistive element, thereby giving option for large displacement measurement. However, one problem in this kind of situation is that while making such helical coils or even such single turn, generally we take one small flexible pad like this, and the resistive coil is wound around this one. I should not draw this way. Resistive coil is wound around this, something like this, and then this flexible pad is bent to form the single turn, or if required multi-turn potentiometer. So, the resistive coil is wound around this one with maybe these are the two end points for final voltage measurement. So, as the contact moves over this, at a particular instant of time, the contact may be maybe touching this particular element, and the next instant with small rotation it is touching this one. Now, from the first coil, this one, to the second turn, it is not a linear change, but there is a certain portion of the coil the slider is not at all coming in contact with. So, the change in the resistive value is more like a staircase kind of thing, but the value of this staircase or the height of each of the stairs can be kept very small or to negligible amount by choosing a proper resistor coil, and also the choosing this particular dimension of the pad suitably. So, potentiometer is the most common instrument for measurement of both linear and angular deflections. Now, potentiometer can primarily be of two types. One is the linear taper potentiometer, the one that we are talking about, where the resistance is proportional to the distance travelled between the position of the contact and one terminal of the device. Here, when voltage ratio must be proportional to the distance travelled or angle covered by the slider, we use this. But there can be another option also, which is referred as a logarithmic potentiometer. Here, the output voltage is a logarithmic function of the slider position. We can achieve that either by using a material whose resistivity keeps on changing along the length, or a resistor whose resistance tapers from one end to other. Now, how we can achieve this? Remember what relation we use between resistance and the dimension of the resistor wire. We know that R is equal to rho into L by A, or R is inversely proportional to the cross section area. Therefore, if this is a resistor coil and if we keep on changing the cross section area from one end to the other, suppose if we keep on increasing the cross section in this direction, then the resistance will keep on decreasing. Accordingly, it will be giving you a tapered measurement of the deflection. This kind of logarithmic potentiometers are particularly used in audio amplifiers because our sense of hearing goes in a logarithmic way, and that's why the logarithmic potentiometer can be a good choice there. Potentiometer, despite theoretically being a zero order instrument, it can deviate from zero order behavior quite significantly because of the presence, because of several factors, some of which we have mentioned that time itself. Like when the slider keeps on moving over the over the resistor, there can be noise, there can be lots of frictional losses, wear and tear, aging. If the contact is, we want the contact to move very rapidly, it may bounce off the contact. The ideally resistor coil should not have any inductance and capacitance, but practically it is not possible to find any conductor which has zero inductance and zero capacitance, and so those effects can also come into play sometimes. And something that I shall be talking shortly is the current drawn by the resistor itself. The frictional losses, also the noise etc., can be eliminated or at least minimized by using the damping contact oscillator, where the potentiometer slider is allowed to, potentiometer is allowed to be filled with some kind of damping fluid, some kind of high viscosity fluid, so that as the contact moves, it suffers strict resistance from the fluid, thereby eliminating the losses and also the noise. We can also use contact coated with some kind of elastomeric damping material, and similar other techniques can also be employed. Now we go to this particular point, current drawn by the resistor. We are saying that we are applying certain kind of voltage, and now this is your resistor coil, and as the sliding contact keeps on moving over this, we get the output voltage. But here we are getting this output voltage, that is fine, but somehow we have to measure this V out, and then only we shall be able to get an idea about the displacement. And how to measure the V out? Of course, we have to use some voltage measuring instrument like a voltmeter, and that voltmeter itself has some kind of resistance. Depending on the value of the resistance, your instrument will also draw some current, and as it is drawing some current, then the output voltage will keep on decreasing based on that. So, there will be some loss. Let us do a bit of calculation for this. Let us draw one small potentiometer. Let us say this is the source voltage, and this is the, sorry, I should draw in a continuous way. So, this is the resistor, and this is the position of the contact at a particular instant. And to measure the output voltage, here we have connected one voltmeter which itself is having a resistance Rm. So, Rp is the total potentiometer resistance. The length of the resistor is xt, and this particular resistance this particular distance is given by xi. Say Vex is the excitation voltage and V out is the output voltage. So, we have to see how this output voltage V out is being modified or affected by the presence of this Rm, or maybe the relation between Rp and Rm. So, we can modify this circuit to represent like this. So, this is your source voltage, then this is the left out portion of the resistance, potentiometer resistance, this is the portion which is in contact with the slider, and this is the Rm that we are talking about. And now we can combine these two into one equivalent resistance. So, this is your R equivalent, this is Rp into 1 minus xi upon xt. We are not considering any kind of tapering, we are considering an uniform resistance of the resistor. Then what is the net resistance? Okay, let us first try R equivalent. R equivalent refers to two resistance, one is Rm and other is Rp into xi upon xt, they are in parallel to each other. So, very standard we can calculate Rm into Rp into xi upon xt divided by Rm plus Rp into xi upon xt. This is the value of R equivalent, and so the total resistor R will be R equivalent plus Rp into 1 minus xi upon xt, that is the total resistance that is prevalent in this circuit. So, R equivalent expression is there. So, let us take Rp common from this. So, we have 1 minus xi upon xt plus from this expression this we have Rm into xi upon xt divided by Rm plus Rp into Xi upon Xt. So, this is the total resistance that is present in the circuit. Here the voltage is V out, if I write properly. Let us say I is the current that is flowing through this circuit. So, your I will be equal to, oh sorry, this is not V out, this is the Vx, and V out is a voltage that is prevailing here. So, Vex divided by the total resistance of the circuit is your current. Let us say this current I, which is coming here, that gets divided into two components. One is this Im going to the voltage measuring meter, and other is say I1. If we draw that particular portion of the circuit, the current gets divided into these two components. So, this Im passes through this Rm, and this I1 passes through this remaining portion whose resistance is Rp into Xi upon Xt. So, what will be your Im? Im will be equal to I into Rp into Xi upon Xt divided by Rm plus Rp into Xi upon Xt. This is how we calculate the value of Im. And now, how much will be the output voltage then? The V out should be equal to Im into Rm. So, let us put all the expressions into this. So, putting Im, we have I into Rp into Xi upon Xt divided by Rm plus Rp into Xi upon Xt. This is Im, which we have just written, into Rm. Now, I is, as per our earlier definition, I is V excitation by R, and R is this particular quantity. So, let us let us make a bit shorter. So, let us take it as V out divided by Vax. There is the ratio of output voltage to the excitation voltage. Then what we have here, let us just try to simplify this entire thing. We have Rm Rp into Xi upon Xt divided by Rm plus Rp into Xi upon Xt into R. R is a big expression that we have already got. So, it will be 1 by Rp into 1 minus Xi upon Xt plus Rm into Xi upon Xt by Rm plus Rp into Xi upon Xt. So, we have to simplify this big expression. Let us multiply this entire denominator with this quantity, or let us simplify the denominator. So, what we have is, in the numerator we have left with, or there is no change in the numerator, Rm Rp by to Xi upon Xt, and in the denominator we have, we can cancel out one Rp, that is this one and this one cancels out. So, this goes off from this. We have only Rm left in the numerator into Xi upon Xt, and in the denominator now we have Rm plus Rp into Xi upon Xt into 1 minus Xi upon Xt plus Rm into Xi upon Xt. So, we have to simplify this, lots of calculations we are doing, but I am still, instead of directly writing the expressions, I am doing all these steps so that you can get the idea about how to reach the final calculation. Let me erase this part to make some space. So, So, how we can simplify this? Let us say, so Rm xi minus xt cancel out, and what we are left with in the numerator, we are still having the same quantity Rm into xi upon xt, and in the denominator we have Rp into xi upon xt into 1 minus xi xt plus Rm. And if we divide, now this whatever we have in the numerator, we are dividing everything by the numerator. So, in the denominator what we are going to get, we are making the numerator 1. So, in the denominator xi upon xt cancel out. So, we are getting Rp by Rm into 1 minus xi upon xt plus xt upon xi. So, it is a very interesting expression to have. Look at this, earlier what we told? Earlier we told that to have the perfect zero order behavior, V out by Vx should be equal to xi upon xt, that is when we have the ideal zero order behavior. But now in the actual scenario, when the Rm is coming into picture, we have this. Now, in which situation these two will be equivalent to each other? That is the situation when this Rp by Rm that tends to 0, then you will be having V out by Vx to be equal to or to approach xi upon xt, which is the ideal behavior. That means this is the ideal scenario, the ratio of Rp to Rm should be tending to 0, or the resistivity of the resistance of the potentiometer should be very small compared to the meter resistance. Now, practically it is never possible for the meter to have infinite resistance. So, practically it is possible only when this Rp is very small compared to the Rm. But again, a smaller value of Rp will affect the sensitivity of the instrument, and therefore, we have to go for some kind of trade off here. That is, the value of Rp should be chosen such that we have for a given Rm we can have a certain level of sensitivity as well as a certain level of error, or we can minimize the corresponding error that is present, that can be present there. What can be the effect of this? Like suppose if we plot this, we have the V out by Vex on one axis and xi upon xt on the other axis. When we have this particular scenario, then it will be a perfect straight line like this. This is the ideal curve. So, this is the scenario when Rp upon Rm is equal to 0. However, as Rp by Rm this ratio keeps on increasing, your curve will deviate from this and it will follow pattern somewhat like this. So, this is the direction on which this Rp upon Rm that keeps on increasing. So, while in the ideal scenario we should have this particular curve, in actual case we are getting a deviation, and that deviation is governed by the ratio of this Rp upon Rm. So, the gist is that why you will want a high value of Rp in order to have a high sensitivity for the instrument, and the value of Rp still has to be very small compared to the meter resistance or the voltage measuring instrument. This particular effect is called the loading effect, means the effect that is being brought in by your measuring instrument, in this case the Rm. This effect is called loading effect, and it can be very important. In a nutshell, you can say that once you are given with a potentiometer, you have some idea about the value of Rp, then you should choose your voltage measuring instrument to have a suitable, to give you a suitable value of this Rp upon Rm ratio. Depending upon the value of Rp, your value of Rm should be selected. So, that is it for potentiometer. Let us try to get some idea about one small problem involving potentiometer. Now, here our problem is, we have the resistivity for a potentiometer where is given, the cross section area is also given, you have to find the potential gradient if 1 ampere current is flowing through the wire. Let us say K is the potential gradient. Now, how we have defined this? We have defined this as the excitation voltage divided by the length of the resistor, and again your how the Vex is related to the current. This is related as I into R, where R is the resistance. So, and R is known as rho L by A. So, let us put it here. So, we have I upon L into rho L by A, which leads to the cancellation of this L. So, we are left with rho I by A. Now, all these parameters are given. Your rho is 5 into 10 to the minus 6 ohm meter, your I is given as 1 ampere, area is given as 6 into 10 to the minus 4 meter square. If you put all this value, I have got this calculated for you. So, our value is 8.3 into 10 to the power minus 3 volt per meter. So, this is the potential gradient of the instrument. Here I am throwing another problem to you. A potentiometer has a wire of length 8 meter and the resistance of the wire is 20 ohm. It is now connected in series with a cell of EMF 2 volt and an internal resistance of 2 ohm, and we also have a rheostat. Rheostat is basically the arrangement which will measure the output voltage, and there will be this connected to the sliding contact. Now, you have to find the value of the resistance in rheostat when the potential drop along the wire is 20 microvolt. This should be capital V actually, it should be microvolt per millimeter. Now, if we write it properly, how to solve this? Okay, I am leaving this one to you. Try to solve this, otherwise in the next class I shall be discussing about this one. But let us quickly move to the next instrument in our line. Another resistive instrument, but a very advanced one, which is resistance strain gauges. The operation of strain gauges again based upon the change of resistance with the change of length. But strain gauges are very important instruments because such gauges are used for measurement of several other parameters, like I mentioned earlier. Several such strain gauges are used for measurement of pressure, temperatures, etc. So, strain gauges are very important instrument, but their working principles are very simple. We know that for a resistor, again R is equal to rho L by A. So, if any of these three, that is resistivity or length or area changes, R will also change. So, the change in R dr can be written as, by simple differentiation, is rho dl plus L d rho minus rho L dA divided by A square. It is simple differentiation that we are doing here. DL refers to the change in the length of resistor, dA refers to the change in the cross section area of the resistor, and d rho is the change in the resistivity. Now, initial volume of the resistor is A into L. Now, what will be the final volume?